All right, welcome back, Marauders. This video is about the nature of energy. This is the start of chapter 5, which is thermochemistry. So in thermochemistry, we're going to be talking a lot about heat and heat transfer during chemical reactions. So as you may have noticed, during a lot of chemical reactions, heat, which is a form of energy, can be released or absorbed. Really common to think, the easiest example is probably just a candle burning. Any kind of combustion reaction, you have heat being released. So there's energy stored inside the chemical bonds, and as those chemical bonds change during a chemical reaction, they release, or in other cases, absorb energy. And that's why thermochemistry is so important, because a lot of energy can be transferred during chemical reactions. So at the beginning of this chapter, we talked just about energy in general. Energy comes in a couple different forms. What energy is it's the capacity to do work or transfer heat. It comes in a couple different forms. We're going to be talking mainly about transfer of heat. Energy can be used to do work. You'll talk about that a lot more in physics next year. But for our purposes, most of what we deal with is going to be involving heat. So what is work? At the beginning of the chapter, they talk a little bit about work, just so we understand all the different types of energy available. Work is the energy used to move a mass against a force. So if you lift your book up into the air, or if you try to push your car down the road, you're using energy because you're moving a mass, the car or the book, and you're moving it against a force. Heat, the type of energy that we're going to talk a lot more about, is the energy used to cause a temperature change. And this is good, and we're in chemistry labs, we're going to find it pretty easy to measure how much heat is released or absorbed during a chemical reaction by measuring the temperature change of the system or the surroundings. So a little bit more about energy, a couple different forms of energy. There's kinetic energy, and kinetic energy is the energy of motion. You've probably heard about this before. When a car is moving down the road, it has kinetic energy because it's moving. In chemistry, atoms and molecules are in motion, so they have kinetic energy. So even like in your book, it looks like it's still, it's just sitting on your table, but the particles that make up that book are actually moving around, bouncing around off of each other, and they have motion, so they do in fact have kinetic energy. Generally, as things get heated up at higher temperatures, they get more kinetic energy. The particles that make up the materials bounce around more and have more motion, more kinetic energy as temperature increases. Potential energy is the energy of position. So if you lift your book up into the air, it has potential energy, which can be changed to kinetic energy if you let it go. It has kinetic energy because of its position relative to other objects. So your book lifted up above the floor, its relative position to the earth, and gravity can act on it and pull it back down to the earth and change that potential energy into kinetic energy. How does this come into chemical reactions? Well, in chemical bonds, you have particles, charged particles, that are attracted and repelled from each other, and electrostatic potential energy is due to the interaction of these charged particles. So this equation, we'll look at this a little bit more later on in some later chapters, but the amount of energy is equal to K, which is just going to be a constant, and then Q is the charge of one of the particles, times Q2 is the charge of the other particle, so it's dependent on the charge of the particles. The higher the charge of the particles, the more attracted they're going to be, or the more energy they'll have, divided by the distance, or how far apart they are. So you have a really strong attraction when you have highly charged particles close together. You'll have a lot of electrostatic potential energy. Okay, so the main thing here is just different types of energy, kinetic versus potential. So motion and potential energy is position. First law of thermodynamics, most likely you've heard of this before. Energy, just like matter, is conserved. That means it's not created or destroyed. Okay, so we have a certain amount of energy. It's not getting more, it's not getting less. It's just transferred from one form to the other. Heat, thermal energy, can be used to create, to do work. Okay, you could change the potential energy into kinetic energy. These things can change from one form to another, but it's not created or destroyed. There's a fixed amount, and we can just transfer it from one form to another. So how do we transfer it? Well, by doing work. So if you push your car up a hill, then you are doing work. You're pushing it some mass up a distance, and you are changing it into, or you're giving it potential energy. or exchanging heat. Okay, so if you put a pot of water on the stove, you can change the energy that's stored inside of the methane molecules into heat, and you can transfer that into the water and make the water hotter. Okay, so first law of thermodynamics, very important that energy is not created or destroyed. So energy can't be created or destroyed, but it can be transferred. So delta E is the change in energy. So when you're looking at a particular system, you can look at how its energy changes over time. It can change by either releasing, absorbing heat and doing work, or having work done on it. So the change in energy of a system is equal to the heat put in or out and the amount of work put in or out. So for heat, we use the letter Q, work is W, and delta, whenever we see the delta, it means change. The change in the amount of energy in the system is going to be equal to how much heat is put in or out and how much work is going in or out of the system. Whenever you use the negative sign, it means they're going out. And if you use the positive sign, it means it's going in. So if you have a delta E that's positive, it means that system is absorbing energy by either absorbing heat or having work done on it. If delta E is negative, that means it's losing energy. So that means it's passed its heat onto the surroundings, or it's done work on the surroundings. Fortunately for us in chemistry, most of the problems we look at are going to involve little or no work being done. So we'll pretty much ignore work. You should be aware that it can, that chemical reactions can do work. Like imagine your gasoline burning in your car engine. It's taking the potential energy stored in the gasoline and it's releasing it to form kinetic energy and to move your car along. We're not going to talk very much about that in this class. We're going to talk mainly about heat. So if we talk about gasoline burning, we're going to assume that it's not being burned in your engine, but it's being burned and giving heat off to the surroundings. So we're going to look mainly just in terms of heat, but it's still a way of measuring the total amount of energy if we are in situations where the work is very small or not doing any work. So we have a name for this. It's called enthalpy. Delta H is the symbol we use for change of enthalpy. And this is the heat flow during a process. So it's pretty equivalent to the amount of energy exchanged during a reaction if we assume that little or no work is being done. So you can think about these kind of interchangeably. Enthalpy, which is delta H, is kind of like the energy of a system, and how much energy is released or absorbed is basically how much enthalpy is released or absorbed during a process.